Today on How It's Made. Aluminum canoes. Wooden stave bowls. Wheelchair accessible vans. And marimbas. When World War II ended, an American manufacturer of fighter jets needed to land new business. The factory employed the same stretched aluminum process used for shaping aircraft wings and came up with an aluminum canoe. No fighting machine, the aluminum canoe is designed for a peaceful day at the lake. Among watercraft, the aluminum canoe is the strong, silent type. It resists breaking and cracking when it comes up against a rock or any other underwater object. So this is one invention that is unlikely to sink into oblivion. Aluminum itself is too soft for canoe construction, so metals like magnesium, nickel, and silicone have been added to give it the needed strength. Factory employees unwind the aluminum alloy onto a work table. Using electric shears, they cut it to length. They lift the metal sheet onto a mold of part of the canoe hull. They clamp the metal to a hydraulic system and activate it. It pulls and stretches the aluminum alloy sheet to the mold, and it conforms to its shape. The molded sheet needs trimming. So they transfer it to a work table and place a template over the contoured section. They clamp it into place. With a scribe, one of the workers etches the pattern onto the molded aluminum. The team then transfers the aluminum sheet to a jig and cuts out the pattern following the etched outline. They shape and cut a second part exactly like the first. The two symmetrical halves will form the hull of the aluminum canoe. They bake the hull halves at 390 degrees Fahrenheit for 8 hours. The heat strengthens the aluminum and adds rigidity to it. Out of the oven, a member of the team now aligns two halves. It's a perfect match, so he now lowers a large clamp. Once in place, he turns a crank to pull the two parts of the aluminum canoe together. Now tightly clamped, he welds the two parts along the bottom. This joins them with a watertight seam. With hand clamps, he tacks the two rounded ends together and welds here. He links the end welds to the one on the bottom, and the result is one continuous leak-proof weld from bow to stern. Next, the team positions an aluminum keel along the bottom seam. They reinforce it from the inside with the T-bar. They drive rivets through the T-bar, hull, and keel to secure the assembly. They install substantial aluminum guards on the bow and stern, using rivets to secure them. These guards will protect the end welds. They brace the base of the canoe from the inside with 6 aluminum ribs. Welded, riveted, and with a good support structure, this aluminum canoe has really taken shape. They equip the rim of the canoe with aluminum gunnels, pounding them with a rubber mallet to improve the fit. Then, a worker rolls non-skid paint on the inside so it won't become slick when wet. They bring incandescent heat lamps in, and the paint dries quickly in the warm glow. After just 30 minutes, the paint is dry. Then it's time to see if it will float. They transfer the aluminum canoe to a tank of water. They clamp a bar across the canoe to apply nearly 1,000 pounds of pressure, more than the weight of 2 people. They check for leaks, especially around the rivets. there are none. Crossbars and bench seating complete the fabrication. There's one last bit of business, and that's the company insignia. This aluminum canoe is now ready for recreation. 10 hours in the making, the fun has only just begun. Bowls have existed for thousands of years. Very early bowls, used to serve food or drink, have been found in China, ancient Greece, and in certain North American cultures. Modern bowls can be made from a variety of materials, such as ceramic, plastic, metal, and wood. Wood bowls come in many shapes and sizes. Many different kinds of wood are used to make bowls, such as rubber wood and teak. Acacia is also a type of wood used to make bowls. Workers cut flat planks of acacia using a large circular saw. The acacia was cut a few days ago in nearby plantations. Planks are cut to thicknesses required for bowl production and pre-dried on pallets spaced apart for better air circulation. Using a table saw, a worker cuts the wood planks, now kiln-dried, into pieces long enough to make the bowl wall. Another worker uses a tilted table saw to cut the wood into shapes resembling a cone. Drying the wood eliminates water that might cause cracking later on. A worker trims the pieces, giving them the angle they need so the staves can be rounded later on. Another worker smooths the rough side of the staves with a spinning cutter. This also helps shape the wood pieces. Another employee lines up the staves on a table before applying glue. She spreads a wood bonding glue onto the sides of the staves. Once they're thoroughly covered with glue, she begins assembling the bowl by sticking the sides together. She assembles a few pieces at a time, handing them to another worker, who arranges the bowl shape by leaning the staves against a centerpiece. They continue the process until all the staves are in place. Then they'll squeeze the staves tightly together. They stretch elastic bands around the outside of the eventual bowl. The elastics, held in place by a steel ring, squeeze the staves firmly against each other. With a hammer, she lightly taps the staves into place, making sure they are flush against each other. She turns the bowl over to make sure none of the staves around the top rim are sticking out too far. She then leaves the bowl to dry. About 5 hours later, they remove the elastics and again leave the bowl to harden for a full day. A template is attached to the eventual bowl in order to cut a circular opening for the bottom piece. The template serves as a guide during the cutting process. A worker moves the bowl around, allowing the cutter to create a perfectly sized hole for the bottom section of the bowl. It's made of the same kind of wood, in this case, acacia. A worker applies glue to the edges of the bottom hole and to the outer edge of the round piece that goes in the bottom of the bowl. He inserts the bottom plate and uses a hammer to force it firmly into place. After another day of hardening, a worker places the bowl in a lathe. With a variety of knives, he begins shaving off the wood. He starts on the inside wall of the bowl. Then he shaves the outside of the bowl, gradually giving it shape. He then uses sandpaper to smooth the surface of the bowl. Another worker then uses a lathe to sand the surface of the bowl. He makes the surface as fine as possible. He must have a keen eye for detail in order to make the bowl surface perfect. A worker sprays a foodstuff varnish onto the surface of the bowl. Several layers are applied, with drying and polishing after each one. If required, a stain is also applied. They place a sticker identifying the manufacturer on the bottom of the bowl. A worker then packages the wood bowl. With the bowl secure, the only thing tossed around will be the ingredients you put in it. The minivan was designed with families in mind, but it also revolutionized travel for people in wheelchairs. Retrofitted for wheelchair accessibility, the minivan offers unprecedented mobility. No need to wait for special wheelchair transportation when there's a minivan in the driveway. Convert a minivan and change a life. A wheelchair accessibility conversion offers the convenience of a ride anytime. From the outside, the van will look no different, but inside the modifications will be major. The total revamp starts with the removal of the van's middle and third row seats. They pull out the carpet and completely strip the vehicle from the front seats to the back. Underneath, a technician saws off the exhaust system and disassembles the rear suspension. The entire undercarriage behind the engine is about to be reconfigured to make way for a new lowered floor. The team also removes the 20-gallon fuel tank. They'll replace it with one of the same capacity to fit the new configuration. They cut out a large section of floor and relocate displaced wiring. They're now ready to roll the new floor framework into position below the vehicle. This steel structure replaces the original one and is strong enough to support the additional weight of a wheelchair. A motorized one can weigh as much as 4 adults. They slide the new steel floor into the vehicle and lower it into the framework. The new floor is significantly lower than the one the van came with, and it increases the wheelchair passenger's headroom by about 10 to 15 inches. After installing the new fuel tank, suspension, and exhaust systems, they return to the interior. A technician fits and binds carpet under padding to the van. He installs the carpet and clamps it while the adhesive cures. With the back of the van rebuilt and carpeted, they now ready the wheelchair ramp. A technician applies a gritty material with an adhesive backing. He simply presses it to the ramp and smooths out any air bubbles. This gritty material will provide a slip-resistant surface for the wheelchair to move across. He attaches a handle and installs 2 cable assemblies to connect the handle to the ramp latches. He attaches a return spring to the handle assembly. He turns the handle and tests the latches to confirm that the mechanisms function properly. The team then links the wheelchair ramp to the new floor with a long hinge. They install stainless steel trim over the hinge to protect it, and also connect the counterbalance cables to the ramp. Hidden springs at the end of the cables provide tension to significantly lighten the load for the operator. The ramp weighs about 130 pounds, but the operator ends up lifting just 15 of that due to the spring-loaded tension. They reinstall the interior plastic panels and repurpose the original second-row seat belts. As they finish up inside, an employee puts the company name on the door of the vehicle. The wheelchair-converted van is now ready for a test drive. The operator unfolds the ramp. He folds away the new seats to make way for the wheelchair. He extends the tie-down belts and attaches them to the wheelchair. He wheels the passenger into the van, locks the wheelchair brakes, and ties the chair to the floor. There are standard seat belts to fasten, and then it's time to sit back and enjoy the ride. Seated in the converted minivan, the individual can now experience the freedom of the road. The marimba is a musical instrument similar to the xylophone, except with a wider and lower range of notes and metal resonators underneath the keys to amplify the sound. While the xylophonist uses hard rubber mallets, the marimbist usually strikes the wooden keys with a variety of mallets, covered with wound yarn. The marimba keyboard is chromatic, meaning it includes all the semitones of a musical scale, the equivalent of the 12 white and black keys on a piano. Each wooden key has a resonator, an amplification tube underneath, tuned to the same note. When the mallet strikes, the resulting vibration causes the resonator to hum that note, transforming the otherwise thin, muted sound into a louder, richer tone. The keys are fashioned from Honduran rosewood, which is hard and dense, yet elastic. After cutting the thickness and width, they set the dial of this custom-made saw to the note they're making, which positions the wood to be cut to the correct length, no measuring required. Next, using a router, they round off all the edges. When a key has sharp edges, it's more likely to chip or splinter when struck, even though marimba mallets are soft and frequently covered with wound yarn. The next step is to drill holes at the nodes, which are specific non-vibrating points on the key. The nodal holes are for the cord that'll suspend the key over its resonator. Now, a computer-guided milling machine sculpts a very precise arch in the underside. This roughly tunes the key. To fine-tune the key, they must tune the fundamental note, plus the first and second overtones, the subtler notes that sound simultaneously with it. When the tuner strikes the key, an electronic machine reads the exact frequency of the vibrations. He repeatedly taps, takes readings, and sands the arch until the fundamental and overtones are pitch perfect. They seal the wood with lacquer. This protects the key from moisture penetration, which would alter the key's tuning. For each key, they make a resonator out of brass tubing. The lower the note, the wider and longer the resonator. Some are so long, they must be J-shaped or U-shaped to fit under the keyboard. To make those curves, workers use short-angled pieces of tubing to join longer, straight pieces. They divide the resonators in groups, then bolt each onto a painted steel rail. There are 6 groups of resonators on this full-range marimba. The instrument is nearly 10 feet long. The ends of the frame are height adjustable. Between the frame ends, a center pole receives the 6 resonator sections, arranged shortest to longest. Then, running over the resonators, wooden cross rails suspend the parts to support the keyboard. Under the lowest and longest keys are those curved resonators fashioned from angled soldered pieces of tubing. Posts mounted in the wooden cross rails support the cotton cord running through the key's nodal holes. At the end of each resonator is a patented tuning plug. After using a lathe to shape a piece of hard plastic into a cylinder with the required diameter, they saw off a slice about the size of a hockey puck. They then quarter the slice, running the cuts just 90% of the way through. These slots make the plug flexible. Next, they drill a threaded hole through the center to the same depth as the slots and wrap the edge in polyethylene gasket tape. The tape smooths the surface, helping the plug glide easily into the resonator. Then they thread a wing screw into the center hole and insert the plug into the corresponding resonator. To tune the instrument before playing, you move the plug up or down until the note is the exact same pitch as the key above. Then, you turn the screw to push the sections outward, locking the plug in position. Everything from this point on is in the Marimbas' hands. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.